All right, so once again, we're going to look at Newton's three laws, forces. Kind of a little bit different situation though here, because we're going to have some strings attached to our objects, which is just basically going to be how our force is being applied. So we have a diagram here. Examine the following diagram and find the force, tension. Forces in strings or ropes or wires are often called tension, so it's the same thing. So I'm going to find the force or tension in each string, connecting the carts. Again, perfect world here where we're assuming there is no friction for now anyways. All right, so using Newton's second law, which is F equals ma, what I'm going to do here is first, I'm going to put that down, F equals ma, is I'm going to look at this system as a whole, all right? So look at everything in general. So again, our net force that's applied to this entire system is going to equal ma, or in this case, the total mass, so I'll put mt there, times the acceleration. And it looks like here we're going to the right. So, all right, now the total mass, if I added it up, of my three objects. Let's see here. I got 1 kilogram plus a 1.5. So I'm at 2.5 kilograms. Well, I add a half. So now I'm at 3 total kilograms. All right. Now these objects are moving horizontally. And as I said here, I've got my mass and I want to find the tension in each string. So let's see here. I've got, well, this is one rope and we'll figure that out. The force is 12 newtons on this rope, but I want to know T2, the tension on this rope, and T3, which is the tension on our third rope. All right, and again, T1, I already know the tension on this rope is 12 newtons. Now, to figure out the tension in these two ropes, I need to know, because the acceleration of each car. And the acceleration of each car is actually the same because they're all moving along together. Otherwise, we'd have a bit of a train wreck. Now, in each object here, so I'll call this the object number 3, 2, and 1. For each of them, the formula F equals ma applies. So the force is equal to mass of item 3 times A. The force here, which I'll call F2, F1, or F3 here, is equal to mass 2, because this is mass 2, times A. Well, I guess I don't need to know anything here because I already know the tension in this string. Now, in the total system, I know the mass of all these cars is 3 kilograms. I want to find the acceleration of this entire system because, again, all these cars are going at the same or accelerating at the same rate. Now, my net force horizontally is not going to be 12 newtons. In fact, our net force is going to be this pink line that's pulling the carts horizontally. All right, and so, again, I'm going to use trigonometry here to find out that net force. All right, so again, I got a triangle here. This 12 newtons is my hypotenuse. This here would be my adjacent. So I'm going to call that my net force. All right, and so again, a little trigonometry. That's my adjacent. So I have cosine of 60 degrees. All right, is equal to that net force. Horizontally anyways. I could have called it F of H, I guess, horizontal. Divided by our hypotenuse, which in this case is 12 newtons. And as usual, I like create my fraction equaling a fraction. And so that my F net, the applied force horizontally on all 3 cars, because this rope here is pulling all 3 of them. Let's see here. So I got 1 times F net is F net, and then I got cos 60 times 12. So I type that into my calculator. Where is it here? There it is. I get a nice flat 6 newtons. All right, so now I'm going to substitute my net force, 6 newtons. I'm not going to worry about direction here because we're just worried about the magnitude of the tension. And clearly this force is pulling to the right. 6 newtons to the right. This mass of this system, they're all 3. And so I'm looking for my acceleration. All right, I shouldn't put an arrow in there because, again, we're just finding the magnitude. Well, if I divide both sides by 3, every car, again, the A's are all the same because they're all moving at the same rate. 6 divided by 3, these are all moving at 2 meters per second squared. That's how fast they are accelerating. Now, that is going to allow me to find T2 and T3 because I'm looking for the force that's applied to this cart. Well, the force that's applied to the cart is the tension. So F2 is equal to T2. Similar over here where F3 is T3. The force is coming from the wire. That's why this cart is moving. And so when I look at my formula here, F2 equals M2 times A. Well, that means T2 is equal to mass 2 times A. Well, T2 then is equal to the mass of this cart, which is 1.5, times the entire system's acceleration, which happens to be 2, because again, they're all accelerating at the same rate. And so this rope pulls with 2 times a half, or 2 times 1.5. Well, that's 3 newtons. All right, because this string or rope or wire, whatever you want to call it, is only pulling 2 carts. Now, T3 is pulling only 1 cart. And again, I'm going to use this formula here. F3 is equal to M3 times A. But again, F3 is equal to T3. So T3 is equal to M3 times A. And again, I'm suspecting this tension is going to be lower because there's less mass. And we're pulling at the same acceleration. So this mass is 1 of this cart. Again, all of these cars are accelerating at a rate of 2 meters per second. And so the force applied by that string or wire is 2 newtons. So our first string is pulling at 12 newtons, but it's on an angle. 6 newtons of it is being pulled horizontally to pull all 3 cars. This T2 string only has to pull with 3 newtons because it has 2 cars. And our last string only pulls with 2 newtons because there is 1 car. All right, so that again is using Newton's second law to apply it to an entire system. Kind of a different little puzzle there. Now, it gets a little more complicated, of course. We get to our next example, where a 2 kilogram block is placed on a smooth level table. Ooh, we have kinetic friction here of a coefficient of 0.4. So you know what, before we even get going here, that means my mu k here is equal to 0.4. We just talked about friction, right? All right, and it's attached by a string passing over a frictionless pulley, perfect world here, to a 6 kilogram mass hanging freely over the edge of the table. Find the tension in the string. All right, so we have a force. All right, now we have 2 objects. I'm going to call this object number 1 and this object number 2. Now this tension for this block is pulling to the right, because I think we all know that this block is going to move this way, and this block, 6 kilogram block, is going to move downwards. Now this tension though, although it's pulling the 2 kilogram block to the right, the same string, so this is the difference here. We got the same string here, is going to be pulling up on the block. Although it's not going to win because something is pulling down on this block, which is our force of gravity, which, as I went through, is always mass times acceleration, but it's a specific acceleration. It is mg. And you know what? I might as well figure that out while I'm here. This is a 6 kilogram block. And the acceleration due to gravity is 9.8 meters per second here. And let's see here, that equals, if I multiply them out, get the calculator here, we got 58.8 newtons. All right, so we figured that out. Now, let's see here. I want to get all the forces. So the tension's pulling up on this one. The string is pulling up on this block, but gravity's pulling down. The string's pulling this block to the right. Kinetic friction. So there is friction moving this way. Just drawing all the forces on here. So that's Fk there. All right. Now, here's another important fact. Very important key here. Let's write it in red. That we have two accelerations. All right. These objects are going to be accelerating at the same rate. So this is object number one, as I've said. Right. So it's going to have a mass 1, which is 2 kilograms. It's also going to have an acceleration, so an A1. This is object 2, as I've said. It's also going to have an acceleration of A2. Now, these objects are going to accelerate at the same rate, except for here's the difference. This block is accelerating to the right, which I've always said is positive. This block here is accelerating down, which I've always said is negative. So these two accelerations, in terms of magnitude, are equal. But in terms of the directionality, they're opposites. Because one's going to the right and one's going down. All right? Now, here we go. So I've got things set up. I want to find the tension. I found the force of gravity. You know what? I need to find this Fk before I get moving on here, the force of friction. And now, again, the force of friction, we just looked at that formula. I got a hand raise here. That's my first hand raise, I think, ever, man. Nobody ever does that. Okay, go ahead. I can't hear you. Am I missing something here? Oh, okay. All right, thought I had a hand raise. Raise her again if you still have your question. All right, I don't hear anything. Okay, so again, we got to find this force of friction. I want to find out everything I can. And again, it's going to be mu k times our normal force. All right, but again, here's the key with this, finding kinetic friction, is that mu k, it told us that, 0.4 here. So I got that. Now this is, again, Newton's first law, using all his laws here. The normal force, right? When I look at the normal force here, that is a force that is always perpendicular to the surface. It is pushing up on the block, so I'll put it up on the top. Now that's our normal force. Now because this block is not going anywhere, the net force is 0. And so there's a counteracting force of Fg. And so my normal force and my force of gravity are equal. Otherwise, this block would be going up in the air. Now, horizontally, it's moving, but vertically, it is not. And so that means that Fn and Fg have to be equal. And so that means our Fn is equal to m times g. All right, now I can keep going here and actually solve that. So let's see if I can slip that in there. So it equals, we got 0.4 times the mass of this object, which is 2, times the acceleration due to gravity. There we go. Oh, it fits. Beauty. Equals, I multiply those three numbers, and I'm getting, let's see here, 7.44. Right? That seemed a little off. Let me try that again. 9.8 times 2 times 0.4. Yep. Oh, 7.84. Okay, 84. Yikes. Thought that was a little off, but I thought it was off more than that. All right. So here we go. Now I'm going to look at each object individually. So let's go with object number 1 here first. All right. So object 1. Now, again, Newton's law, our net force, F equals, we're going to have, I look at my purple arrows, The tension pulls it to the right, but I'm going to subtract the force of friction. So I better, let's see here, put in net. This is our net here. I can't really write that. And this is our FK. And again, I subtracted because FK is moving in the opposite direction. Now, my net force on this particular object, again, using Newton's second law, it is mass times acceleration, or in this case, the mass of object 1 times the acceleration of object 1 is equal to T minus my FK. All right, so let's see here. Now, my mass is 2. The acceleration, yeah, I don't know that. Just filling out what I do know. T, that's what we're trying to find out here, is the tension in the string. FK, I figured that out, is 7.84, which makes me look like I messed up my note, my completed note. All right, that's all I got for this. That's all I can do. I'm going to solve for accelerate. I'm going to leave it. How's that? We'll just leave it. All right. Now I'm going over to object 2 because that's all I got here, this formula. Problem is here I got 2 variables. Yikes. All right, so now I go over to object 2 and do an analysis of what's going on with it. All right, so again, I'm going to look at the F net, which I could write a little bit better, but what's going on here? T is pulling it up, so I'll go positive T. Gravity's bringing it down. All right, so I'm going to subtract, and I already know what gravity is. It's 58.8 there. All right, now, F net. Again, just like I did over with object 1, it's going to be mass times acceleration. And again, it's going to equal our tension minus gravity, which is 58.8. Now, again, this mass is of the second object, and the acceleration's of the second object. And so, again, I'm going to sub those values in because I know the mass. I don't know A2, though, do I? No. All right, now, 6 times A2, I'll have to put that in after, equals T minus 58.88. Now, again, 8. So, again, there is A2. All right, now here's the trick. All right, I've got 2 equations here, but I have 3 unknowns, which is a bad news. So there's one equation. Whoops, there's our second one. Right, I have 3 variables. I got a T, I've got an A1 and A2, but look at this. I can get rid of one of these variables because here's the deal. A1 is the same as negative A2. All right, so, or I could say the negative A1 is equal to positive A2. The idea here is they're opposites of each other. All right, so now here's what I'm going to do. Instead of, well, I'm going to keep this equation, but now I'm going to substitute in here, instead of an A2, I'm going to replace it with a negative A1. So now this second equation is becoming negative 6 A1. I just moved the negative sign in front of the 6 is equal to T minus 58.8. All right. So again, now I got 2 equations, 2 unknowns. Little grade 10 math coming your way. 2 equations, 2 unknowns. I'm going to solve systems of equations here. So you can use substitution or elimination. Now with elimination, our variables have to line up. So let's see here. I got a coefficient here. I've got a 2A1 equals T minus 7.4. Let's see, the T's line up. So I'm going to put equation 1 down here. Now, a little bit of a trick here, because what's B? The acceleration of both masses. So what I can do when I'm solving systems of equations, I'm going to find the acceleration and the tension at the same time. All right, so again, I'm going to write down equation number 1 here. It's 2A1 equals T minus 7.84. Now, when I'm using elimination, and I'm going to end up eliminating T here, and the coefficient in front of the T is a 1, so they're the same. So I'm going to subtract these 2 equations, which means I'm going to subtract the A1, subtract the T, subtract the numbers. Whew. Okay, so here we go. Negative 6A1 minus 2A1. That's a minus 8A1. All right, then I take negative, going to get the calculator here, negative 58.8. I subtract minus 78 or 7.84. Yeah, minus 70.84. Now I got two negative signs come together. Negative and negative give me a positive. So I'm going to do negative 58.8 plus 7.84 because two negatives give me a positive. And I end up with negative 50.96. All right, now I'm going to divide both sides by negative 8. All right, and so my A1 acceleration, which means, let's see here, I'm going to have a negative divided by negative. So this thing is going to accelerate to the right because it's positive, which makes sense, right? So I take that 50.96, divide it, or negative 50.96, divide it by negative 8, and I get 6.37 meters per second squared. So A1, it's moving to the right. A2 would be positive if it's moving up, but look at it's negative 6.37, right? So that means this object is accelerating down. Makes sense. But that's not what we're trying to find. We're trying to find the tension, right? Well, we have two formulas for tension. We have this one here, or we have this one right here. I can use either or. So I'm going to use this one here because it's out of the way. And again, I'm going to use the fact that A1 is 6.37. So subbing back in, 2 times, because now I do know what A1 is, 6.37, equals T minus that 7.84. All right, so now let's have a look here. 2 times 6.37 is 12.74 is equal to T minus 7.84. All right, solving equations. I'm going to move that 7.84, or negative 7.84 over to the other side, which, of course, when it changes sides, changes sign. And if I add those two numbers together, equals T. Equals T. There we go. All right. I put those two numbers together, and that is the force that the string is going to be pulling on both objects. And let's see here. I add them together. 12.74 plus 7.84. All the force going on here. And I get 20.58 newtons. And so that is the force that this string is pulling on this 2 kilogram object to pull it to the right. It's also the force that this rope is pulling on this 6 kilogram object upwards. But again, so gravity is much stronger and hence pulling this block. Well, A1 is telling us this first block goes to the right. And because A2 is negative of that, it tells us this block is going down. Because there is situations in physics where you're not really sure because of slopes and sizes which way the system is going to roll. All right. In this case, I think it was obvious, but But there we go. So that, again, is applying Newton's laws using friction in there. Stop recording. Not like it even matters.